formal synthesis, including explainable synthesis. And with that, Hazem, thank you for joining us.
Thank you, Russ, for the kind introduction. And I'm glad to be here today and give you a glimpse on the work that we have been working on with respect to reactive synthesis. So in my talk today, I will introduce the problem of synthesizing approximate implementations for reactive systems and present both automata theoretic and symbolic algorithmic approach to the problem. So this work is joint work with Rainer Dimitrova and Bernd Finkbeiner from the CISPA Center for Information Security. So from all the talks that we have, from all the exciting talks that we have heard so far about the reactive synthesis problem, we know that synthesis comes with this big advantage of allowing us to synthesize implementations automatically from their specifications. And these implementations have the nice feature that they are correct by construction. So we have guarantees on that they satisfy the initial formal specification. But this particular means that the tasks of developer is shifting from implementing a system to providing and designing specifications for that system, which is in itself a difficult task. So users have to make sure that their specifications are right, and that in fact there is an implementation that satisfies these specifications. So particularly in reactive systems, we say that a specification satisfies, an implementation satisfies a specification pi if for all possible sequences of input values, the outputs produced by this implementation satisfy the specification. So one important and one crucial idea here is that the user has to provide a lot of knowledge about the environments in which these implementations will be operating, and in general, without this these assumptions on the environment or without this knowledge, we might end up quickly with specifications that are unrealizable. So with the approximate synthesis problem, we're raising the question, in case the specification is indeed unrealizable, can we still find an implementation that at least satisfies the specification approximately? So more concretely, we're concerned about the problem that, can we find an implementation that satisfies the specification on a given class of inputs that are generated by the environment? Or even further, when we think about it in its quantitative way, are we able to provide an implementation that satisfies the specification on at least a specified portion of the sequences given by the class that we're interested in? So let me give you an example on that. So assume we have a specification for an arbiter, and let's say the arbiter is serving two clients that are sending requests to access the shared resources via the signals R1 and R2. And then the arbiter decides to grant them access via the signals G1 and G2. So, and the specification requires that only one of these clients enters the shared resource. So one part of the specification will include the property of mutual exclusion, where only one grant at a time is given to the client, to each of the clients. But we also want to have a fair arbiter. So we need to make sure that if there is a client requesting to access the shared resource, then this client will eventually get a grant to access the shared resource. And lastly, we want to make sure that the clients are not kicked out of their shared resources while they're still using them. So the last property that we have in our specification is one that says that a grant should not be revoked while the client keeps requesting it. So let's say we gave a grant to client I, and client I is still requesting the access to the shared resource. And we know that client eventually will release its grant, then we should keep allow the client to remain in its shared resource. So in other words, as long as the client uses the resource, we are not allowed to kick that client out, but of course under the assumption that it will leave resource eventually. So by looking at the combinations or conjunction of all these three properties that we would like the arbiter to fulfill, unfortunately, this type of specification is unrealizable. And the simple reason for that is it could be that we have the case that after gaining a grant, the client might never lower the request and will not allow the second specification, for example, to be realized in the implementation. So although one of the clients is asking to enter the shared resource, that client will never get the chance to enter that shared resource. Now, we can fix this because in general, it's not that the environment, there are no restrictions on the environments that these systems are operating in. So for example, we could say that the system is operating environment where we know that each client is eventually going to release the grant within a fixed bounded number of steps, or it will stay there forever in the sense that this client becomes unresponsive. But if the client comes unresponsive, then it's okay to kick the client out of the shared resources. And having this assumption on the environment will make the specification immediately realizable. Because now we can just wait a fixed number of steps, namely those given by the bound on how long a client might remain in the shared resources. And then if the client exceeds this bound, we'll just say, okay, client became unresponsive, and then we just revoke the grant and allow the second client to enter the resource. Now the question is, how can we specify that? So there has been several works on how to add assumptions to the environments. So many of these approaches will extend the specification itself with properties, new properties that define exactly these assumptions on the environments. There are a lot of been work on doing so. Some of the work relied on a counter-example guided approach to add these types of assumptions. There has been also work on looking at the counter strategies of the environment in a refinement loop, and then based on these counter strategies, add new formula or new requirements to the specification that will make the specification realizable. There are other approaches that tend to have assumptions on the structure of strategy, of environment strategies. So for example, we could have the assumption that we know that the environments are presented by strategies of bounded size. So we're restricting the behavior of the environment by restricting the syntactic structure of these environments. And in my talk today, we're moving along the lines of adding structural assumptions on the environments, but in a new way, namely by saying, instead of bounding the size of the environment or the strategies of the environment, we're gonna bound the input behavior of the environment. So the size of input sequences that are produced by the environment. And this idea is based on the key point that if we are dealing with environment that have a bound on their structures or bound on their size, for example, then we also know that they have a bound on the shape of inputs or the size of inputs that they're producing. More concretely, since we know they're to refine it, we can characterize the behavior of these environments by the set of input sequences that are defined as ultimately periodic word. And this is what we will base our approach on today. So the main ingredient of our approach is that we say that the inputs generated by the environment are represented by ultimately periodic words, and then we define a bound on these ultimately periodic words. So on the length of representations of these ultimately periodic words, and we call these representations lassos. So lassos define a pair of two input sequences. So we have the stem u and then the period v. And then we say that a lasso is of size k if the total length of u concatenated with v is less or equal to k. And then the input induced by this lasso is the one given by the ultimately periodic word u v omega. And now the synthesis problem becomes this question on, can we find k lasso precise implementations that satisfy our property. So what this means exactly is if we have a specification phi, we're looking for an implementation that satisfies the property phi on input sequences that are representable by lassos of length at most k. And in its quantitative version, so in its quantitative variant, we'll just add the portion on which this implementation of the portion of inputs on which this implementation should satisfy the property. So here we're talking about epsilon k approximate implementations. And by that mean, okay, we want to have an implementation that satisfies P on at least 50% of the inputs or 90% of the inputs of that can be represented by lassos of length. Okay. And in the first part of my talk, I will take first a look at the qualitative problem. So we look at the synthesis problem again, but now we have a new input, namely the length of the input lassos. And then what we're looking for is if the spec is not realizable, then is it at least realizable on the given class of inputs representable by k lassos. All right, so I will start with an automata-based algorithm on how to solve this problem. And then I'll move later to see how we can encode that in a symbolic way using quantified Boolean expressions. And after that, we'll move to the quantitative variant of the problem and see how we can solve that problem as well. So let's start with the automata-based approach. So the idea of the automata-based approach is, again, we want phi to satisfy the inputs representable by at most k, of length at most k. And for all the other behaviors, the implementation may behave arbitrarily on the inputs. So the specification may violate, the implementation may violate the specifications for input behaviors that are only representable by lassos larger than k. So more concretely, the language that we're looking for, or the language that should be described by the automaton that we're looking for, is one that, considering phi, we first separate phi into these two spaces. The first space is one that defines input behaviors representable by k lassos and the complement set of that. And then what we are interested in is in over approximating this problem. So we're looking for an automaton that defines the language of k lassos, so inputs of that representable by k lassos, and over approximates the rest. So the precision is then based just on the set of k lassos. We need to make sure that violations on k lassos are not accepted by the automaton, and all the others are accepted by the automaton. All right, so how do we construct such an automaton? We do that in two steps. So assume we are giving a deterministic parity automaton that describes the specification we're interested in synthesizing, or in synthesizing implementation for. So the first step is to characterize the set of k lasso input sequences. And we do that by constructing a DFA that accepts a word or a prefix word if it's a prefix of one of these k lassos. And now, having characterized this set, what we do is we compute a product between the set, this automaton defining these prefixes, and the original automaton defining the specification. So, and having done that, what we'll end up with, we'll have an automaton that represents exactly this over approximation set here. And this automaton accepts everything that originally satisfies the property phi. Or if it doesn't, then it at least have to be a prefix of something that is rejected by the automaton AK. And rejected by just refers to the fact that, again, we're dealing with lassos that are not representable by lengths of less or equal to k. All right. So having acquired such an automaton, then solving the problem becomes as we solve any synthesis problem on these types of automata. We'll interpret the deterministic parity automaton that we constructed as a tree automaton, and then we play the emptiness game on that tree, and then the result means that we have a k lasso precise implementation for phi, or the problem remains unrealizable in case we haven't found such an implementation. So we show that the size of this prefix automaton is exponential k, and there's a matching lower bound for that. So the total complexity of this composite automaton is polynomial in the original automaton defining the specification, and exponential in the bound k on the lassos. All right, so, and this is exactly what this theorem states here. So with respect to LTL specification, we remain double exponential in the length of the LTL formula, and we are exponential in the bound k, which is the new input to the problem. All right. So in addition to this automata theoretic approach, you also provide a symbolic approach. So we're solving the bounded synthesis problem for k lasso precise implementations here. So we have another parameter that sets a bound on the size of implementations we're interested in. And then the result is, well, we'll get a k lasso precise implementation with n states. Since we already have an automaton that defines that, we can, of course, use bounded synthesis as presented by Bernd Finkbeiner and Sven Schewe, which means that the constraint system will be exponential in phi, and in the so for LTL formulas will be exponential in phi, and in k. We propose a more direct approach on how to encode that using quantified Boolean formulas. And I'd just like to show you the main idea on how this encoding looks. And the encoding itself is polynomial in the LTL specification and in the bound k. All right, so the main idea is that we're searching for an implementation of size n, such that for all input lassos of length k, the corresponding outputs produced by these input lassos satisfy the property phi. So for the implementation, we encode the transition relations and the output labeling. Here we define lassos as done in the bounded model checking encoding of length k, and then we also need to define the several loop start positions of these lassos. And then we need another formula that does this matching. It matches the outputs that correspond to a certain input lasso in the current implementation that is under consideration. And the size of such an encoding is linear in the formula, and then quadratic in both the size on the implementation and the bound on the lassos. All right. Now, lastly, I want to also tell you a little bit about the synthesis algorithms or the algorithmic approach for epsilon k approximate implementation. And let me just give you a motivation why these types of approximations are important. So it could be the case that we still have specifications even after bounding the size of the lassos for which we will not find an implementation. So these type of problems will remain unrealizable. So let's say, again, we're looking at an arbiter, and then we have the variables for request and grant, but we also have a variable that plays the role of a write signal, so the permission to give a grant or not. And we have the formula that tells us that each request should be answered with a grant, but of course, a grant can only be given if the P signal is true. All right, so this formula tells us as long as every time if the P signal is not true, then we're not allowed to give a grant in the next step. And even if we bound the number of lassos, this is unrealizable. In fact, just look at lassos of size 1, where the signal P is always false. So in this case, we will not be able to produce a grant to allow the client to enter the shared resource. So here we move towards a more quantitative question. So saying that, okay, it is true that this is also unrealizable for bounded lasso, but can you give me the optimal implementation, or is there an implementation that at least satisfies on a ratio of input lassos? And you will see here, if we look at lassos that were input lassos where we exclude this one lasso where we only have not P, then we'll end up again with a realizable implementation. So we reformulate the problem to the following. So in addition to k and n, we also have this parameter epsilon. And now we're looking for epsilon k approximate implementations with n states. And then giving an epsilon what we want an implementation that satisfies this following equation. Namely, we'll look at the number of lassos representable by input sequences which satisfy phi to the total number of possible lassos. So the total number of possible inputs from the input sequences from the environment. And then we want to compute an implementation that maximizes this fraction here. So what we show is we can
Hazem, just a quick note that here's your friendly timekeeper that we are now at 20 minutes. So if you can maybe.
Yeah. I need 1.5 minutes, Ross, if that is okay. Yeah. Okay. So the key idea here is that we can encode this problem, this approximate synthesis problem, as a maximum model counting. It's namely one where we want to maximize over the number of implementations of size n. And we want to count over we want to, let me see. Yes, we want to find an implementation of size n that maximizes the number of inputs for which the specification is satisfied. Sorry for the formulation here. So this can be formulated as a sub-problem, but where we have variables defining the implementation of the implementations we're interested in, and we have another variables that talk about the inputs that we're satisfying the formula over. And then what we do is, instead of just looking for satisfiable assignments, we are looking for assignments that maximize over the number of inputs that are satisfied, and then existentially quantify over the implementations that satisfy these inputs. So the total size of this equation is again linear in the formula, and it remains quadratic in both n and k. We have implemented a prototype for that using the KQBF solver and the max count tool, which was implemented also, was implemented by Daniel Fremont, Markus Rabe, and Sanjit Sechia. And there is a trade-off between these tools. So there were some solutions that were solved by the QBF solver Cake, could not solve by max count, and the other way around. But in general, the instances also become quickly very large. So improvements both on the QBF solvers as well on the maximum model counting tools will make the problem itself more scalable, hopefully in the future. And with that, just let me quickly summarize. So I introduced the problem of synthesizing approximate implementation, more precisely K-lasso precise implementations. And I presented explicit automata-based approaches as well as symbolic approaches. And then we also took at the quantitative version of that, where we were able to reduce that to a maximum model counting problem, where we applied the maximum model counter max count, and were able to get at least approximate implementations in case the solutions remained unrealizable. I would like to refer you for more technical details to our paper, as well as a follow-up paper on the complexity of constructing automata that represent these approximate languages that I talked about here. And with that, I would like to thank you for listening.
Thank you. Is there a question that people could ask either directly or into a Q&A? In the meantime, Hazem, if you can stop sharing so that Suguman can share her talk.